In an ideal environment, all of these traps might function equally well. They all have the facility to trap steam and remove condensate. Unfortunately, no steam trap operates in an ideal environment. Friction, corrosion, and erosion are all detrimental to the trap's ability to conserve live steam. The operating principles themselves will determine how fast the trap responds to changing condensate loads and how well the trap seals under non-ideal or intermittent conditions. The standards and materials used in manufacturing the trap also affect its service life. Steam systems themselves are dynamic. They are turned on and off, subjected to varying load demands, use water of questionable and varying purity, and often operate in freezing temperatures. Therefore, there are a number of operating conditions that must be considered in evaluating a steam trap's performance for any particular job. For each condition, we will rate the trap in one of three ways. Green indicates that the trap performs well and is recommended under the condition outlined. Red indicates that the trap is highly susceptible to problems if operated under the stated condition and is not recommended. Yellow means that caution should be applied in using a particular trap if the condition exists. The trap may operate marginally under one condition, but perform so well under another that its use is acceptable with an increased PM schedule or if protective devices are installed. One of the first evaluations should concern the amount of live steam lost through the trap when it's new. All trap types condense some steam due to thermal radiation, but live steam is discharged from some types even when new because of the way they are controlled or sealed. The water seal prevents live steam loss through the IB and the primary orifice of the DC. Disc and bellows traps prevent live steam loss by closing in the presence of steam or condensate near steam temperature. F&T and DC traps pass live steam mixed with any air they vent. While this loss is greater than with other traps, it is generally considered acceptable in applications which require the venting of large air accumulations. Production rates, ambient temperature, and steam quality are just a few of the factors which vary the condensate load to the trap. The operating principles of each type trap determine the nature of its response to varying condensate loads. The mechanical traps, the IB, DC, and F&T, are continuous drainers. They are controlled directly by the amount of condensate entering their bodies, and therefore respond immediately to any load changes. Thermostatic and thermodynamic traps react to changes of temperature or changes of state rather than responding directly to the presence of condensate. All traps are required from time to time to handle the heavy air and condensate loads of startup. At startup, the system is cold, devoid of steam, and often has large accumulations of condensate and air in the lines. F&T and bellows traps are most recommended for frequent startup conditions because of their ability to handle large air loads. The F&T and bellows traps are wide open at startup and remain open until the system nears operating temperature. The manual metering valve of the DC provides a controlled bleed for startup air loads. The small bucket vent of the IB trap is sized to prevent live steam loss, but may cause temporary air binding during startup. The addition of a thermic vent to an IB passes large startup air loads, but closes to conserve energy when the system reaches operating temperature. The disc trap closes when any gas, including air, moves across the bottom of the disc. The air trapped above the disc does not condense and takes time to bleed off. In a situation with frequent startup or heavy air loads, disc traps are not recommended because they take too long to evacuate the system of non-condensables. Back pressure is the pressure in the condensate line which opposes the supply pressure. It is created by such things as pipe friction, flash steam, differential valves, or receiver relief valve settings, and elevated condensate return lines. For every 2 feet of condensate elevation, approximately 1 pound of back pressure is created. Back pressure reduces the differential pressure across the trap. Since the differential pressure across the trap provides the force for drainage when the trap is open, the best any type of trap can do is operate at a reduced capacity when the back pressure is increased. An increase in back pressure to a disc trap increases its cycle rate. If the cycles become fast enough, the trap may reach a point where it machine guns. Back pressure may increase to the point where the trap remains open, blowing live steam. Where high or fluctuating back pressure occurs, the disc trap is not recommended. Steam traps must be sized to handle the heaviest loads they might encounter. When production is down or demands on the system are low because of the season, traps may be subjected to loads far below their design limits. The trap must continue to discharge condensate as it is formed and trap live steam in the system even under these low load conditions. The IB and DC compensate for low load situations by operating in a condition known as dribbling. Whenever the valve cracks open, condensate flashes across the valve seat. Because of the volume and velocity increases that accompany this flashing, there is a sudden pressure drop in the orifice throat, resulting in an increase in differential pressure across the valve. If the entering condensate flow doesn't provide a sufficient water level under the bucket to counteract these increased closing forces, the valve snaps shut. F&T and bellows steam traps have modulating outputs at very low loads. In these traps, the opening and closing forces tend to balance out as the load decreases and the trap doesn't fully open or close, but modulates with the condensate flow. The disc trap is not recommended in situations where the average load is less than 3% of the trap's rated capacity. Live steam causes the trap to cycle frequently, prematurely wearing the seating surfaces. As condensate flows through the system, it picks up dirt and scale formed on the walls of the piping, as well as any solids that carry over from the boiler. Traps must be able to operate in the presence of this dirt without damage to or blockage of their orifices or mechanisms. The intermittent discharge of IB and DC traps create a self-scrubbing effect at the bottom of the trap. Dirt particles smaller than the orifice diameter are flushed from the system. With the orifice located at the top, dirt, scale, and other matter settling to the bottom of the trap will not plug the discharge port. The bellows trap may be oriented in any direction. When the valve is located at the top, this trap also resists clogging. Since the trap modulates on low loads, however, care must be taken that dirt large enough to lodge in the throttled opening doesn't enter the trap. The bellows trap in any other orientation and the F&T trap have valves in or near the bottom where dirt can accumulate, blocking the orifice. In addition, the small openings, when these traps modulate, are easily blocked open or closed by small dirt particles. The disc trap cannot be recommended in the presence of dirt either, because it has two sealing surfaces, both of which must be perfectly flat. The intrusion of dirt between the disc and seat not only provides a poor seal, but also aids erosion of the seat and disc surfaces because of the high velocity flow between them. The installation of a strainer immediately upstream of any trap will protect it, provided the strainer is properly maintained. Carbon dioxide is the primary non-condensable found in steam systems. Condensate and carbon dioxide coexist when temperatures in the system are at saturation. When the temperature drops below saturation, however, the two combine to form carbonic acid. This acid is extremely corrosive and will eventually eat through piping and equipment. Oxygen is another gas trapped in steam systems which speeds up corrosion. Not only should a steam trap operate in the presence of non-condensables, but it should also discharge them at or near steam temperature to prevent the formation of corrosives. The bucket vent of the IB and DC traps pass non-condensables through the water seal, where they are vented at or near steam temperature during each trap discharge. The F&T traps air above the condensate seal and vents it through the thermostatic valve mixed with some live steam 15 to 20 degrees below saturation temperature. The disc and bellows traps can both back up condensate. Although this subcools the condensate and air mix, there may be advantages to some systems in using the sensible heat in the water that outweigh the risks of corrosion. Water hammer can be a very destructive force. Water, like steel, is incompressible. It doesn't give. Hydraulic, thermal, or differential shock can send 100-pound columns of water accelerating toward a trap with devastating results. Although well-designed systems minimize the occurrence and severity of water hammer, its effects on a trap's performance must be considered in many situations. Traps that are designed to resist these damaging forces are recommended where water hammer is likely. The disc trap has no parts which can fail from this sort of shock. The IB and DC traps use open floats with the same internal and external pressures, making these resistant to water hammer. The same cannot be said for bellows or F&T traps, however. The fixed internal pressures in the float and bellows elements make them likely to collapse when subjected to these pressures. One of the most common uses of steam is to heat a product or maintain its temperature in a freezing environment. In these applications, when the system is shut down or when pressure is lost for a period of time because of a line or component failure, condensate can be subjected to sub-freezing temperatures. Even with the best insulation and installation procedures, the ability of the trap to resist damage from freezing should be considered for this service. Freezing conditions require a trap to withstand abnormal pressures, the results of which are much the same as with water hammer. The IB, DC, and disc can withstand some freezing without trouble, with the addition that the stainless steel IBs can actually expand under severe conditions and still operate after they are thawed. The more delicate bellows elements and the float in the F&T can be crushed if they retain condensate in their bodies when temperatures drop below freezing. The final, and probably the most important requirement, is service life. The service life of a steam trap is the amount of time it operates efficiently, conserving steam and removing non-condensables and condensate from the system. The benefit of long service life is lower operating expense. Generally, savings are realized from reduced energy consumption, repair or replacement costs, and downtime for maintenance. Obviously, all of the other requirements we've spoken of contribute to the overall life of the trap, along with the materials chosen for the trap and the care taken in its design and assembly. Both the IB and DC have excellent service life. They have low initial steam loss and respond favorably under the conditions we've looked at. Although the DC discharges some live steam mixed with the air in order to purge non-condensables, it handles large air loads better than the IB. The F&T trap is most often used on modulating systems because it is a continuous drainer that handles startup air loads and light condensate loads well. It may have a good service life if caution is taken to prevent damage to the trap in systems where dirt, freezing, and water hammer are likely to occur. Bellows traps can also have a good service life provided they are protected against water hammer. They can be piped in any orientation, and they have good startup characteristics. Bellows traps do back up condensate, however, and the increased corrosion and water hammer potential may be a problem. The service life of the disc trap is expected to be short. Under heavy loads, the disc trap backs up the condensate, and on light loads, the high velocities through the orifice, as well as the violent impact of the disc on the seat, make the trap especially susceptible to wear. There is a proper trap available for any steam system. By balancing the requirements of your product with the conditions in your system, you can determine the trap most suitable for your application.